Okay, in this video we're going to go through the previous quiz, and I'll walk you through the solution. So we here have a mixture problem where we have a company manufacturing two models of MP3 players, a 10 gigabyte model and a 5 gigabyte model, and we have information about how many hours of labor each one requires to assemble and how much electronic work is required, and we're given information about the profit made from each model. So the very first thing that we should do is construct a mixture chart. So what we have to identify first is how many rows will be in our mixture chart. Well, that has to do with the number of products, right? We introduce a variable for each product. So in this case there are two products, right? Namely the 10 gigabyte model of MP3 player and the 5 gigabyte model. So we will have two rows in our table. So we'll have the 10 gigabyte. Now we need to introduce a variable, right? Because the issue at stake is how many 10 gigabyte models should be produced in a given week and how many 5 gigabyte models should be produced in a given week, given the various resources we have and the constraints that this problem gives us. So we're going to let X denote the number of 10 gigabyte models that should be made in a given week, and Y the number of 5 gigabyte models that should be made in a given week. Right? So that's always the very first step of making a mixture chart, as you identify the products or the objects to be manufactured or to be produced, and each of those is designated a variable. Okay, now we need to know what resources there are. Well, if we go back and look at our problem, we see that on the one hand there's a certain amount of time that's required to assemble the MP3 player. Right? The 10 gigabyte model requires 2 hours of labor for each one, and the 5 gigabyte model requires 1 hour of labor. So that means that we have one of our columns is labor hours, basically for assembly, right? To actually put the various components together. So what do we know? Well, how many hours are available in a given week to do this? Well, it says that for our given company there are only 100 given labor hours available in a week, so we put that at the top of the columns. And now what can we say? Well, each 10 gigabyte model requires 2 hours of labor to assemble. So that's what we put right here in this first column, right? Because that box corresponds to X. It's telling you for each 10 gigabyte model that gets produced how many hours of labor is required to assemble it, and the answer is 2. And likewise for Y, how many labor hours are required to assemble each 5 gigabyte model? Well, the problem tells us 1, so that's what goes there. Now, what else do we know? Well, in addition to needing some amount of time to assemble, before they're even assembled, there's some amount of time that has to go in electronic work and working with the pieces to get them ready so that they can be assembled. So that is our other resource. So that gives us another column in the table. And then we can say, well, what do we know? Well, for any given 10 gigabyte model, how many hours of electronic work are necessary? Well, we see in our problem each 10 gigabyte model requires 4 hours of electronic work. So 4 would go here. So it's saying, right, that's the row that corresponds to X, the 10 gigabyte model, corresponds to the 10 gigabyte model, and we're saying each 10 gigabyte model requires 4 hours of electronic work. And for Y, we see that it requires 3 hours of electronic work. How many are available in a given week? Well, 240. So you should think each of these columns is giving us a constraint, right? It's giving us a resource and a constraint. Namely, for example, the first column, one of our resources is labor to assemble the various pieces. And we have a constraint. We only have so much labor time available in a given week, in this case 100 hours. And likewise, another resource we have is so much time of work on the electronics, and we only have 200, but that also has a constraint. We only have 240 hours in a given week available for that. And finally, we always have a column for profit. So reading the last paragraph, we see that the 10 gigabyte model can be sold for a profit of $7 each one. So 7 goes in that box. and each 5 gigabyte model can be sold for a profit of $5, and so 5 goes there. So once we've actually constructed a chart like this, a mixture chart, the rest of it is actually pretty easy to do. So we need to write down some linear inequalities that describe this situation. Well, what do we know? Well, the first thing that's usually automatic is we're producing some number of things, right? We're deciding how many models, how many of the 10 gigabyte models to produce, that's X, how many of the 5 gigabyte models to produce. So since X and Y are those numbers, immediately one condition that we have is that we want X greater than or equal to 0, and we want Y greater than or equal to 0, right? We're actually producing some number of things. It doesn't make sense for them to be negative, right? We might say, let's not produce any 10 gigabyte models. That's a feasible production policy, but both of them have to be greater than or equal to 0. We can't produce negative amounts. Now, so automatically we get some of our linear inequalities just from the fact that the number of things to be produced must be non-negative. Next, each of our resources, right? We have 2 resources, and they both have constraints and how much resource we have. So that leads to 2 other inequalities, right? So there's a labor inequality or a labor, what we might call constraint, namely the time needed to assemble. So what we would say is we only have 100 hours available. So on the right, we would put less than or equal to 100 because that's the constraint, the total number of labor hours that we use in making 10 gigabyte models and 5 gigabyte models. That has to be less than or equal to 100. 100 is the maximum we have. So what appears on the left-hand side? Well, suppose we're going to make X 10 gigabyte models. Each one of those requires 2 hours of labor time. So if we're going to make X of them, how many hours of labor time are we going to use? Well, 2 times X. Right? Think, for example, suppose we make 50 of them. Right? If we make 50 of them, and each one requires 2 hours, that total together requires 100 hours. So we just multiply them. And same thing for Y, each one requires 1 hour. So we just write it like this. So that's our labor constraint. And then we also have a electronics constraint for time for electronics work. And the same way, the total amount of time we have available to us is 240 hours. So if we're going to make X 10 gigabyte models, and each one requires 4 hours of electronic work, how much total time are we using in producing X 10 gigabyte models? Well, 4 times X. And in the same way, how much time are we using total to produce Y 5 gigabyte models? 3Y, since each 5 gigabyte model requires 3 hours of electronics work. And so those are all of our inequalities. And finally, if we write down our profit function, call it P, then what can we say? Well, if we sell X 10 gig, if we're producing X 10 gigabyte models, let's assuming that we're selling all of them, then that means that we're getting 7x profit from that, right? $7 for each one sold, and we're producing X of them. And in the same way, 5y for the 5 gigabyte. So that's all our information. Now we need to go up and graph this. Okay, so immediately, so let's suppose that, this is our y-axis here, and the other one, the horizontal line, is our x, the bold black horizontal line is our x-axis. Now, let's suppose that each of these squares that we have here, well, actually, suppose each length is about 10, right? So, namely, here's 10, 20, etc., and here's 10 and 20, and so on. So the fact that x, remember our equations, we have x greater than or equal to 0, y greater than or equal to 0, we have 2x plus y less than or equal to 100, and we have 4x plus 3y less than or equal to 240. So to say x and y are greater than or equal to 0 means that we're working in the first quadrant, namely we're working above the x-axis and to the right of the y-axis. So that's fine. Now we need to graph 2x plus y. Now first of all, we need to graph the associated lines. So namely, we want to look at 2x plus y equals 100 and 4x plus 3y equals 240. So probably the easiest way to graph these is to actually think of where they intersect the x and y axis, namely the x and y intercepts. So for 2x plus y equaling 100, we want to know where does it intercept the x-axis. Well, the x-axis is precisely where y equals 0. So if we plug in y equals 0, we get 2x equals 100, and so x would be 50. So that means we go out here 1, 2, 3, 4, 5, right? So this right here at 50 is where it's crossing the x-axis. Now we need to know where it's crossing the y-axis. The y-axis is where x equals 0, so we plug x equals 0 into that equation, and we just get y equals 100, so we need to count up 10 units. That would be up here. And now we just need to connect those with a straight line. So that's the line 2x plus y equals 100. Okay. Now we have to do the same thing for the other line, 4x plus 3y equals 240. We do the same thing. Let's find the x and y intercepts. So to find what crosses the x-axis, we set y equals 0. So we get 4x equals 240, and we can solve for x equals 60. So that would be right here. Here's 60. And now we need to know where it crosses the y-axis. So we plug in x equals 0, and then we get 3y equals 240. So y equals 80 satisfies that, and that would be right here. So then we just need to match those things. So try to draw it carefully in there. And now, so this line here is 4x plus 3y equals 240. Okay. So there we have it, right? We've graphed everything because we've also graphed, remember, we've also graphed x equals y and y equals 0. Sorry, x equals 0 and y equals 0. X equals 0, right, is just the y-axis that's drawn on here. And y equals 0 is the x-axis, which is drawn on here. So all those. Now, of course, now we remember what we really wanted was not just to graph lines. We had all these linear inequalities. And so we need to find the region that the set of all points x and y that satisfies all four of these linear inequalities. So the first two, as I've said before, just mean that we're in the first quadrant where we're to the right of the y-axis and we're above the x-axis. For these two, we need to satisfy that, and you can kind of check that the region we want here is basically the region that's to the left of both of these lines. And so it's this region that I'm kind of shading in red at the moment. So the region that I've shaded in red is the feasible region, right? It's the region of all points x and y that satisfies all four of these linear inequalities. And now what we need to do is identify the corners or the vertices. Well, so let's indicate those maybe in green. So on the one hand, we see we have one here, and that one is easy. That's just the origin, 0, 0. There's one right here, and we can see pretty easily that that is 50, 0. There's one right here, and that is 0, 80. And then finally we see there's one right here where these two lines meet, namely 2x plus y equals 100 and 4x plus 3y equals 240. They intersect at one point, and that's one of our vertices. And so we need to know what is that point. So now we've drawn it carefully enough on this graph that we could actually just read off the coordinates. But let's actually go through and see how to solve this in another way, algebraically, right? Because the problem is maybe you didn't draw your picture carefully enough and it doesn't exactly lie on a grid point, or so it's sometimes useful to be able to solve this algebraically. So what we have is we have these two lines, right? We want linear equations now, just not inequalities, right? Because we're trying to find where these two lines intersect. And now what we could do is say, well, there's different things we could do. We could solve one equation, the first equation, for example, for y, and then plug it into the second equation. Let's do something different this time. Let's multiply the first equation by -2 on both sides, right? Because if we multiply by -2 on one side, then we have to do the same thing on the other side in order to have equality. So what do we get then? So the very first equation becomes negative 4x minus 2y equals negative 200. The second equation we didn't touch. It's still 4x plus 3y equals 240. And now we can think of adding these equations. And the way we add them is we add every term on the left side and we add everything on the right side. So we get negative 4x plus 4x, 0. We get negative 2y plus y, that's a positive y. And on the right side, we have negative 200 plus 240, and so there's just a 40. So right away, we see that y has to be 40. And now we can just substitute y equals 40 in either equation. We can say 2x plus y equals 100, or 4x plus 3y equals 240. 2x plus y equals 100 seems to be a little bit easier to solve. So we have 2x plus y equals 100. That was one of our original equations. We put plug in y equals 40, and we get that. So then we solve. We subtract 40 from both sides, so we get 60, and then we solve for x. 60 divided by 2 is 30. So we see then the point has to be 30, comma 40. Now let's look. Does that actually make sense? Well, here is the point. Here is a 30, x equals 30, and here is x equals 40, and sure enough, you can see that that's our point. So graphically, that makes sense, and algebraically, we just saw that we get the same answer. So this is just something that you can keep in mind, is that if you are trying to find a corner where two different lines meet, if you graph it really well and accurately, then you can just read it off from the graph. Otherwise, you can solve it algebraically. And now we have all four vertices, right? 0, 0, 50, comma 0, 0, comma 80, and 30, comma 40. And now all that's left is to actually plug each of those points into our profit function. So remember, our profit function is 7x plus 5y. And now we have these points of 0, 0, 50, 0, 0, 80, and 30, 40. And so the corner point principle just says we have to plug these 4 points into our profit function and take the biggest, right? And this is because the reason we can do this is because the profit function is a nice linear function, right? X and y show up only to their first powers. We don't have any squares or other kind of complicated expressions. And the region that we're working with is also basically a region bounded by lines. It's what's called a convex polygon. And the convexity is important here. No dents or holes. So just plugging these in, we get, plugging these into P, we get 0, right? If you plug in 7 times 0 plus 5 times 0 is 0. Here we would get 7 times 50 plus 0 times y. And so that would be 350. Doing it for 0, comma 80, we would get 0 times x plus 5 times 80. That's 400. It's a little bit bigger. And then finally for 30, comma 40, we would get 30, we would get 7 times 30 plus 5 times 40. So this would be 210 plus 200 for 410. So we see then that that is the biggest, right? Because we had these 4 vertices or corners, and plugging them into the profit function, we get the possible values 0, 350, 400, and 410. So 410 is the biggest. So that means 3040 is our optimal production policy. That means, right, remember the whole point of this problem was how many 10 gigabyte models should we make and how many 5 gigabyte models should we make in a given week to maximize our profit. So this is telling us then, going down here, to say that 3040 is our answer means that we should make 30 10 gigabyte models and 40 5 gigabyte models in a given week to maximize profit. So that's our answer. That is our optimal production policy. Now, one thing you'll note is that in solving this problem, it was very important that we first made a mixture chart, right? It was a story problem, we took the mixture chart, and that gave us a way of telling us what information is important and what information is superfluous and doesn't actually matter. Then, once we had the mixture chart, it was very easy to get the linear inequalities which describe the problem, and then we had to graph them, and we needed to graph them fairly carefully, and that way we could find the corners. So if you don't graph your problem, it's going to be very difficult, if not impossible, to actually find the vertices. So you need to graph, once you get the linear inequalities, you need to graph the problem, and you need to try to be fairly careful. So you should have some graph paper that you work with on the side in order to be able to solve these problems accurately. If you just try to just not graph it and just not visualize it and just try to do it in your head, you're most likely going to get corners that aren't really there, and you're going to get them wrong, and everything will be messed up. So although it's kind of lengthy, you should follow this process. Make your mixture chart, get your linear inequalities, and then graph them.